Talk about building something truly massive. There is this underlying expectation of physical permanence.
Right. Like it is set in stone.
Exactly. Think about structural engineering for a second. You design a skyscraper.
Yeah.
You dig deep into the earth, you pour a massive concrete foundation,
Yeah.
you bolt the steel framework together beam by beam, and eventually the building just stands there.
It's finished.
Right? It's static. You know exactly how many floors it has. You know exactly how many people can safely fit in the elevator. And honestly, that is comforting. We like things to be visible.
We do. We like them
I like
categorized.
them to be finished. But then you step into the world of modern software and specifically distributed systems, and suddenly that entire skyscraper metaphor just completely falls apart.
It really shatters.
Because we are looking at an architectural landscape that is fluid. It is almost, I don't know, biological.
That's a great way to put it.
Imagine waking up one morning, and suddenly there are a million new people standing on the roof of your building.
Which would be terrifying in the real world.
Completely terrifying. And instead of collapsing under the weight, your building just has to instantly, magically grow 1,000 new floors beneath them.
Yeah.
In real time, without a single person spilling their coffee.
It is the absolute definition of building the airplane while you are already flying it.
Yes.
But you're flying at supersonic speeds, and every hour another 100,000 passengers are trying to board mid-flight.
Welcome, everyone, to you, the curious, the lifelong learner who wants to understand exactly how the digital world operates without getting completely bogged down by impenetrable textbook jargon.
Because there is a lot of jargon.
So much jargon. But that is what we are doing today. The mission of this deep dive is to take an intimidating, highly technical stack of source material and extract the absolute best, most mind-expanding moments.
The aha moments.
Exactly. We have custom-tailored this journey for your time and your curiosity. Today, we are focusing on one of the most astonishing technical stories of our generation.
It really is.
We're talking about Instagram's mind-boggling evolution from a tiny, scrappy startup to an absolute global juggernaut.
It is the perfect case study.
Yeah.
Because it shows that scaling a system to billions of users isn't just about plugging in more servers.
Right. We're just like writing more code.
Exactly. It is a fundamental evolution of philosophy. It's applied mathematics, it's economics, and surprisingly, it is deeply rooted in sociology.
And organizational structure.
Precisely.
Just to tease the sheer scale of the journey we are about to go on today, we are talking about an app started in October 2010 by exactly 3 engineers.
Just 3 people.
3 people running on a single server setup. And we're going to trace how that exact same core concept transformed into a complex distributed ecosystem handling over 1 billion users.
It's a massive leap.
We're going to unpack how they survived sudden traffic spikes like New Year's Eve and how they evolved to process trillions of machine learning signals every single day.
Trillions. It's hard to even conceptualize that number.
And joining me to navigate this is our resident expert, the calm, analytical voice of reason, who is going to explain to you not just what was built, but exactly why it fundamentally matters to your understanding of the technology you hold in your hand every single day.
Well, thank you. I'm very much looking forward to this. When you actually look under the hood of these massive systems, you realize that the apps we take completely for granted,
The ones we just mindlessly scroll through.
exactly, while waiting in line for coffee, they are actually miracles of modern engineering.
Okay, let's set the stage. Because every massive system starts small.
Always.
Before we can even begin to appreciate the wild complexity of things like service meshes and global microservices, we really have to understand the elegant simplicity of the original architecture.
And it was very simple.
In October 2010, founders Kevin Systrom and Mike Krieger launched Instagram. As we noted, just 3 engineers. And looking at their architectural history, the original stack was astonishingly basic,
Yeah, they used AWS EC2 instances.
which were running Ubuntu Linux, right?
Right. And the backend was just a monolithic Python and Django application.
You know, the database. Just
Yeah.
a single PostgreSQL database.
It is almost shockingly traditional when you look back at it.
I mean, it's the exact same setup a college student might use to build a side project today.
It really is. But that was precisely their superpower.
Let me pause and actually unpack some of those terms for the listener, just so we are all on the exact same page.
Good idea.
So AWS EC2 basically just means they were renting standard computers in Amazon's massive warehouses instead of buying their own hardware.
Right. Cloud computing 101.
And Ubuntu Linux is just the operating system running on those rented computers. Nothing fancy. Python is the programming language they wrote the code in, and Django is a framework.
basically a pre-built toolkit for Python.
Yeah, that helps you build web applications incredibly fast without reinventing the wheel. And Postgres is a very standard, highly reliable relational database.
It's basically a giant, highly organized spreadsheet.
Exactly. So they grabbed the most reliable, well-documented, off-the-shelf tools available at the time.
There was absolutely no magic in the individual components. The magic was in how they orchestrated them.
And they handled their early growth, which was explosive. They hit 13 million users by December 2011.
That is a crazy growth curve.
Insane. And they handled that using Amazon's Elastic Load Balancer. That load balancer was fronting exactly 3 NGINX instances.
NGINX being software that just acts as a web server.
Right, taking the incoming requests from the internet and handing them to the Python application.
But the smartest thing they did early on was how they handled the actual photos.
Yes. The media uploads completely bypassed that core server setup.
Which is crucial.
The photos went directly to Amazon S3 for storage, and they used Amazon CloudFront, which is a content delivery network, or CDN, for fast global delivery.
That separation of state is a foundational concept.
Like, get down a bit.
Well, they recognized immediately that handling heavy media files like megabytes of image data would completely choke their application server.
They would just bog down the Python code.
Exactly. By offloading the images to S3 and CloudFront, they ensured that their Python servers only had to handle lightweight text and logic.
So the application servers were only dealing with the metadata.
Right. The user profiles, the comments, the relationships between users, just the little string of text that says, user A liked photo B.
I like to think of this early setup using a real-world equivalent. It is like running a wildly popular, critically acclaimed restaurant out of a single food truck.
I love this analogy.
Your Elastic Load Balancer is the person standing outside the truck on the sidewalk, taking orders, managing the chaos, forming the line.
Yeah, keeping things orderly.
You have exactly 3 cashiers, those are your 3 NGINX instances, taking the orders from the person outside. And inside the truck, you have one incredibly talented, incredibly stressed chef cooking every single meal.
And that chef is your single PostgreSQL database.
Exactly. Everything revolves around the chef.
And following that analogy, the photos bypassing the server entirely, what does that look like?
Oh, right. That is like telling your customers to grab their own canned sodas from a giant cooler sitting outside the truck on the sidewalk.
Oh, that's perfect.
The chef inside the truck doesn't need to waste precious time turning around, opening a fridge, and handing out a soda.
Right. The chef only handles the complex, custom-made meals.
Exactly. The heavy lifting of the drinks, or the photos, is handled by the cooler outside, which is S3 and CloudFront.
It is an incredibly efficient system for a small operation. But, as you know with any food truck, you can only serve so many people before the line goes completely around the block.
And people start getting angry.
No matter how fast that single chef cooks.
Exactly. Which leads to a really obvious question, and one I think a lot of people listening might be wondering right now.
Go for it.
If Kevin Systrom and Mike Krieger knew they were building a global social network, why didn't they just build for 1 billion users from day one?
Yes.
Like, wouldn't it have saved them a massive existential headache later on to just build a complex, distributed multi-database system right out of the gate?
That is the ultimate trap of system design.
Really?
Yes, it's called over-engineering. Building a complex distributed system early on is considered an absolute anti-pattern.
Why is that?
The guiding principle here is honest trade-offs. When you are a startup with 3 engineers, your most precious resources are not CPU cycles, and they aren't gigabytes of memory.
It's time.
Yes, time and specifically cognitive load.
Cognitive load, meaning just how much sheer complexity the human engineers can hold in their heads at one time without making catastrophic mistakes.
Precisely. If those 3 engineers had tried to build a horizontally sharded microservices-based architecture on day one, they would have spent 6 months just configuring network proxies.
Oh, wow.
They'd be dealing with distributed consensus algorithms, managing service discovery protocols.
Stuff the user never even sees.
Exactly. They would have been writing infrastructure code instead of building the actual product features that users wanted, like the actual photo filters and comments.
So by sticking to a monolith and a single database, they maintain speed.
Speed, agility, and reliability.
There is a very clear distinction to be made here between vertical scaling and horizontal scaling.
Yes, let's define those.
Vertical scaling, or scaling up, is just buying a bigger food truck. You go to Amazon, you click a button to upgrade your rented server, you add more RAM, you add more CPU cores to that single machine.
Right. And horizontal scaling.
Scaling out. That's buying 10 separate food trucks and trying to coordinate them all.
And early on, vertical scaling is the economically and practically sound choice. It vastly simplifies state management because everything, all your data, all your logic runs on one single machine.
You completely avoid all the nightmares of distributed consensus.
Exactly. Imagine trying to get 10 different food trucks to perfectly agree on exactly how many burgers have been sold in total at any given millisecond.
That coordination alone takes immense effort.
It does. The discipline Instagram showed in keeping things vertically scaled and incredibly simple is exactly what allowed a tiny team to survive scaling to 14 million users.
It really makes you wonder how many modern startups completely fail because they over-engineer their architecture before they ever find product-market fit.
It happens constantly in the tech industry.
They spend millions of dollars in seed funding building a system capable of handling Super Bowl halftime traffic, but they run out of money before they get their first 1,000 users.
Because the infrastructure was too complex to maintain and too slow to develop, adding microservices and complex network dependencies introduces interactions that fundamentally complicate debugging.
And deployment.
Right. A monolith, while it will eventually hit a ceiling, allows you to iterate rapidly.
So Instagram waited until the monolith was genuinely pushed to its absolute physical limits before they changed the architecture.
They let the actual pain of the system dictate the engineering, which is the exact right way to do it.
And the pain absolutely arrived.
Oh, it did.
So they solved the early growth phase. They kept it simple, but suddenly they face a completely different physics problem.
The data explosion.
Yes. By early 2012, Instagram hit 30 million users. And that single PostgreSQL database, our lone, heroic chef sweating inside the food truck, became a massive bottleneck.
You physically could not buy a server large enough from Amazon to hold all that data.
You couldn't process all those likes and follows. The motherboard literally couldn't hold any more RAM. They had hit the ceiling of vertical scaling.
So they had to transition to horizontal scaling. They needed to split the database.
They needed to master database sharding.
And this is where the engineering narrative shifts from conventional web development, like the kind of stuff you learn in a boot camp, to truly elite, world-class system design.
So sharding simply means they took their single database of user data and partitioned it across multiple separate databases.
Right.
They used something called hash-based partitioning on user IDs to distribute data evenly. This allowed parallel queries and writes.
Yes.
But what is wild is that they didn't just buy 100 physical servers and split the data 100 ways.
No, they didn't.
They mapped thousands of logical shards, which were implemented as PostgreSQL schemas, to a much smaller number of physical servers.
That distinction between logical and physical is brilliant, and we should really break down why.
Please do.
A physical shard is the actual metal box sitting in a server rack in an Amazon warehouse. It has a power cord, a CPU, a hard drive.
Right, the hardware.
A logical shard is just a virtual bucket of data living inside that box.
So instead of making one giant bucket per server, they made hundreds of tiny buckets per server.
Yes. By creating thousands of logical shards, Instagram gave themselves incredible flexibility for the future.
How so?
Well, if physical server A starts getting too full, maybe the hard drive is reaching 90% capacity, they can easily pick up a few of those logical buckets stored on it and move them to a brand new physical server B.
Just lift and shift.
Exactly. And they can do this without having to rewrite their core routing logic. The application still knows the data lives in bucket 452. It just updates its map to say that bucket 452 is now living inside server B instead of server A.
It prevents massive, chaotic data migrations where you have to take the whole system offline.
Exactly.
But the coolest part of this 2012 era was how they handled the IDs for all this data.
The 64-bit IDs, yes.
Think about the volume here. If you have data split across thousands of logical buckets, and your users are uploading dozens of photos a second, hitting the like button hundreds of times a second globally.
Every single one of those actions needs a unique identifier, a serial number.
And it needs to be sortable by time, so your feed shows the newest stuff first. They considered using external tools for this, like Twitter's Snowflake ID generator, but they avoided it.
They did.
Instead, they built custom logic directly into PostgreSQL using a database programming language called PLPG-SQL.
And the specific mathematical structure they designed for that ID is an absolute masterclass in bitwise engineering.
Okay, let's unpack the 64-bit ID structure because it's fascinating.
Go for it.
So they created a 64-bit ID. The first 41 bits were dedicated to a timestamp, representing the exact millisecond since a custom epoch they set in 2011. The next 13 bits represented the logical shard ID, and the final 10 bits were an auto-incrementing sequence using modulo 1024.
Let me jump in and contextualize that really quickly.
Yeah, please.
64 bits is quite literally just a string of 64 ones and zeros. That's all it is to the computer.
Right.
But by mathematically slicing that string up into 3 distinct sections, they packed 3 entirely different pieces of critical information into a single, highly compact number.
Let's try to map this to the real world. It's like a highly specific, magically dense zip code.
Oh, good analogy.
Imagine every single photo uploaded to Instagram gets a stamp. The first part of the stamp, the 41 bits, tells the system exactly what millisecond the photo was taken.
Right.
The second part of the stamp, the 13 bits, tells the system exactly which virtual bucket or logical shard that photo lives in.
Yep.
And the final part, the 10 bits, is the exact house number within that bucket.
And that final part, the sequence, is crucial for high concurrency.
Right. Clarify the modulo 2 and 24 part. What does that actually mean?
Modulo math is basically just remainder math, or clock math.
Clock math.
Yeah, if you have a clock and it's 10 a.m. and you add 4 hours, it doesn't become 14 o'clock. It loops back around past 12 and becomes 2 p.m.
Got it.
Modulo 124 means the sequence counter counts up 1, 2, 3, all the way to 1023. When the next photo comes in, it loops back to 0.
So it's basically a fail-safe.
Yes.
If 2 users upload a photo in the exact same millisecond, and those 2 photos happen to get assigned to the exact same logical bucket, they will still get a totally unique ID because one will be house number 5 and the other will be house number 6.
Exactly.
And because it loops at 1024, they can handle 124 unique uploads per millisecond per shard without ever having a collision.
It is brilliant. The timestamp ensures that you can always sort the IDs chronologically just by looking at the number itself. The shard ID ensures that the piece of data always knows exactly where it belongs in the distributed network, and the sequence handles the collisions.
But here is where I want to push back, or at least ask the question any modern developer would ask.
Ask away.
Why build this yourself? Twitter's Snowflake was a tool specifically designed by another massive tech giant to solve this exact ID generation problem.
True.
And it was an open source tool. Why go through the headache of writing custom PLPG SQL logic directly inside your database when you could just download a tool that already does it?
That decision comes entirely down to the physics of latency and the mathematics of failure.
Meaning what exactly?
If you use an external ID generator like Snowflake, your application has to make a network call to that external service every single time it needs an ID.
Okay.
The Python code says, "Hey, Snowflake server, I have a new photo, give me an ID." Snowflake receives the request, generates the ID, and replies, "Here is your ID." Then the Python application turns to the Postgres database and says, "Okay, save this photo with this ID."
And all of that communication has to travel across actual physical wires in the data center.
Precisely. That network hop takes milliseconds. And more importantly, network connections can fail.
Wires get faulty.
Switches get overloaded, packets get dropped.
Right, assuming the network is perfectly reliable is one of the classic fallacies of distributed computing.
It is the first fallacy. By embedding this 64-bit ID generation logic directly inside PostgreSQL via a stored procedure, meaning the code lives inside the database itself, they eliminated the network hop entirely.
That's huge.
When a row is inserted, the database generates its own ID locally and instantly on its own CPU. It reduces the latency of the operation, and it entirely removes a potential point of failure.
If the database is up, it can generate IDs, period.
Period. It is a profound demonstration of the impact of minimizing network dependencies at scale.
I feel like embedded database logic is almost a lost art in modern web development.
Oh, completely.
Today, developers tend to want to pull all the logic up into the application layer, into their Python or Node or Go code, and they treat the database just as a dumb storage locker. Put data in, take data out.
Which is a mistake at scale.
But Instagram proved that making the database smart and letting it handle its own internal logic saved them massive overhead.
It did. And it ties directly back to their choice of hash-based partitioning over range-based partitioning.
Let's explore that. What happens if you do it the wrong way? What is range-based partitioning?
If you partition by a range, you might say, okay, user IDs 1 to 1 million go to physical server A, and user IDs 1 million to 2 million go to physical server B.
Seems logical enough.
The problem is, you inevitably run into what system designers call hotspots. Imagine a massive celebrity signs up for Instagram today.
Like Taylor Swift or someone.
Right. They get assigned an ID of 1,500,000, so their data lives on server B. Suddenly, millions of followers are hitting server B simultaneously to view their photos, to leave comments, to hit like.
So server B is completely melting down, the CPU is paid at 100%, the memory is exhausted.
Completely overwhelmed.
And meanwhile, server A, which houses the first million users who signed up years ago and are maybe less active, is sitting there completely idle.
Exactly.
The food truck chef on the left is having a nervous breakdown, while the chef on the right is casually reading a magazine.
That is exactly what happens. Hash-based partitioning solves this.
Wow.
It takes the user ID, runs it through a mathematical hashing function, and predictably randomizes where that user's data lives. It scrambles the mapping in a way that is mathematically perfectly even.
Oh, wow.
It ensures a statistically even distribution of traffic across all your servers, completely neutralizing the hotspot problem.
Okay, so by 2012, they've survived the data explosion. The monolith application is still there, but the database is now heavily sharded, handling the immense scale of user data.
Safely partitioned.
But, as always in engineering, solving one bottleneck immediately reveals the next one.
It's whack-a-mole.
The servers aren't melting from storage limits anymore, but they face a completely different physics problem. And this is all about the need for speed.
Databases are fundamentally too slow.
Right. Even beautifully sharded, hash-partitioned databases are too slow to provide the ultimate modern user experience. The frictionless, never-ending infinite scroll.
And this comes down to the fundamental physics of hardware. A traditional database has to read data from a physical disk. Even if it's a solid-state drive, reading from storage is mathematically slow compared to the CPU. You need a memory layer.
Right, reading from a disk is like walking down the street to the library to get a book, whereas reading from RAM, random access memory, is like pulling a book out of your backpack.
It is light speed.
Yes. The physics of disk storage simply cannot compete with the speed of RAM.
To solve this, Instagram introduced a custom tool they called TAO, which stands for the Associations and Objects.
Interesting.
It was essentially a graph database abstraction built on top of MySQL to handle the massively complex web of feeds and relationships, who follows who liked what.
But crucially, for the real speed, they relied on Redis for caching those timelines.
Redis is incredible.
Redis is an in-memory data store. It stored pre-computed user feeds directly in RAM, enabling lightning-fast reads. This caching layer sat in front of the database and intercepted the read-heavy workloads, entirely avoiding the back-end databases for frequent operations. And we are talking about serving billions of image views every single day.
Caching is essentially the art of storing the answer to a difficult question so you don't have to figure it out again the next time someone asks.
Let me hit you with another analogy. Think of caching like a busy bartender on a Friday night.
Let's hear it.
Let's say the bartender has a cellar downstairs with 100 different types of craft beer. That cellar is your database.
Okay.
When a customer orders a rare, obscure stout, the bartender has to leave the bar, walk down the stairs, find the specific keg, pour the beer, and walk back up.
It takes time.
It takes time. The customer has to wait. But if it is a Friday night and everyone in the bar is ordering the exact same popular light Pilsner, the bartender is going to keep a massive cooler full of that specific Pilsner right on ice next to the tap.
And that cooler is Redis.
Exactly. You don't walk to the cellar for the popular stuff. You just grab it instantly, hand it to the customer, and move to the next order.
And if we take that bartender analogy a step further, caching doesn't just happen in one single cooler.
Really? Where else?
There is a deeply layered caching hierarchy designed to protect the database from ever having to do unnecessary work. At the very edge, you have the browser cache on your phone, storing static images so you don't download the same profile picture twice.
Yeah, well, your phone does some work.
Then you have the CDN edge servers, the Amazon CloudFront we mentioned earlier, globally caching content close to the user's physical city.
So a server in Chicago caches stuff for Chicago users.
Exactly. Then you have the application cache, which is where Redis sits in the data center, caching dynamic computations like the personalized order of your feed. And finally, you have the database cache itself built into Postgres or MySQL.
So what does this all mean for you, the listener, when you are swiping on your phone? It is the literal reason your thumb never has to pause and wait for an image to load as you endlessly scroll.
The feed is ready before you are.
The complex mathematical puzzle of what should this user see next has already been pre-computed, solved, and placed in memory before you even open the app.
But here is the catch, and it is a massive one. Cache invalidation is notoriously one of the hardest problems in all of computer science.
Why is that?
Think about the complexity. You have pre-computed a user's feed and stored it in Redis memory. It's sitting there waiting. But what happens if a friend in that feed suddenly deletes a photo or edits a highly controversial caption?
Oh,
You now have stale, incorrect data sitting in the cache.
right. If the bartender keeps the cooler fully stocked with the popular Pilsner, but suddenly the brewery calls and issues a safety recall on that specific batch, the bartender needs to know instantly.
They have to throw out what's in the cooler and go back to the cellar for a different beer.
If they don't, they serve bad beer.
Exactly.
If Instagram doesn't invalidate the cache, you see an ex's photo after they've deleted it, or you see a comment that was removed for violating guidelines.
Instagram heavily relied on the cache-aside pattern to manage this flow.
How does cache aside work?
In this pattern, the application code checks the cache first. If the data is there, a cache hit, great, return it instantly.
It's smooth sailing.
If it is not, a cache miss, the application goes down to the database, fetches the raw data, computes the feed, returns it to the user, and then puts a copy in the cache for the next time.
Okay, so it populates the cache as it goes.
Right. But handling the invalidation, meaning knowing exactly when to delete that cache copy because the underlying database just changed, requires immense orchestration.
How do they do it?
They likely used event-based invalidation, where a write to the database, like a user deleting a photo, automatically publishes an instantaneous message across the network to clear the relevant Redis keys.
It is incredible to think about the economics of this. You're paying a massive premium for memory because RAM is vastly more expensive per gigabyte than disk storage.
It is. But pushing reads to memory fundamentally shifts the economic cost of scaling in your favor.
Because compute is even more expensive.
Yes, buying terabytes of RAM is expensive. But compute time, meaning the actual CPU cycles required to recalculate a complex social feed from scratch thousands of times a second, is exponentially costlier at scale.
That makes sense.
Not to mention database locks, where rows of data are locked during transactions, creating a traffic jam. By paying a premium for Redis memory, they bought back their CPU capacity and saved their core databases from completely collapsing under the weight of billions of read requests.
So reads are handled by Redis. The infinite scroll is smooth. Data is safely sharded across Postgres. The system feels robust.
For a moment.
Right, for a brief moment. But we hit the next wall. And this is a terrifying one. This takes us to around 2014, dealing with global scale.
A whole new paradigm.
What happens if an entire data center catches fire? Or, much more commonly in the tech world, what happens when a rogue construction backhoe accidentally cuts the main fiber optic cable supplying internet to your primary server farm in Virginia?
That happens more often than you'd think.
And beyond physical disasters, how do you handle the massive influx of writes? Not reads, not people just scrolling, but people actively commenting, liking, and logging massive amounts of activity data from hundreds of millions of devices worldwide simultaneously.
The requirements of the system fundamentally changed here. It wasn't just about reading feeds quickly anymore.
It was about ingesting an astronomical volume of event data and ensuring that data survived catastrophe. A single data center was no longer an option.
By 2014, Instagram migrated major parts of their system to Cassandra.
Which is a NoSQL database.
Yes. Cassandra is known for its NoSQL capabilities. They chose it specifically to handle high-rate scenarios like activity logs because it offers better partitioning and seamless replication across completely different physical data centers.
Okay.
They implemented multi-datacenter replication for disaster recovery. So a copy of the data lives on the East Coast and a copy lives on the West Coast or in Europe.
But crucially, and this is the part that really made me stop and think, they used asynchronous syncing between the data centers to balance consistency and availability.
This is the perfect moment to introduce one of the most foundational, inescapable theories in all of distributed system design.
Let me push back first just to make sure I understand the reality of asynchronous syncing.
Go ahead.
The speed of light is fast, but it still takes time for a signal to travel across an ocean. If the syncing is asynchronous, doesn't that mean user A sitting in a coffee shop in New York might look at a viral photo and see 10,000 likes?
Right.
While user B, sitting on a bus in London, might look at the exact same viral photo at the exact same second and only see 9,995 likes because the data centers haven't caught up to each other yet.
Yes, that is exactly what it means.
Is that actually acceptable? Is it okay for the app to just show wrong data?
You have just perfectly articulated the heart of the CAP
Oh,
theorem.
all right.
The CK theorem, formulated by computer scientist Eric Brewer, states that in any distributed data store, you can only simultaneously guarantee 2 out of 3 properties: consistency, availability, and partition tolerance.
Okay, define those three terms for me in plain English, because they sound very academic.
Let's break them down. Consistency means every read receives the most recent write.
So, perfect truth.
Yes. If anyone, anywhere in the world likes a photo, every single other user globally sees that new, instantly. There is one single truth.
Okay.
Availability means every request receives a response, without error, even if it is not the most recent data. The system stays up, it answers the phone.
Got it. And the third one?
Partition tolerance means the system continues to operate despite network failures dropping messages between nodes, like your rogue backhoe cutting the fiber cable between New York and London.
So the theorem says if I have a distributed network spanning the globe, which Instagram definitely does, I literally cannot have all three. The math forbids it.
Exactly, because network partitions, those cut cables, or even just dropped packets due to heavy traffic, are a reality of physics. You cannot prevent them.
So partition tolerance is a given.
Therefore, you must have partition tolerance. Since P is non-negotiable, when a partition happens, you are forced to make a painful choice. Do you want consistency or do you want availability?
If you choose consistency, what happens to the user?
If you choose strict consistency and the New York data center loses its connection to the London data center, New York has to completely stop accepting new likes.
Stop entirely.
Yes, it has to return an error message to the user because it cannot mathematically guarantee that London knows about the new like. You sacrifice availability, the app goes down, or at least that specific feature throws an error. You prioritize truth over uptime.
And if you choose availability?
If you choose availability, New York keeps accepting likes. It shows users its local version of the total count, even though it knows full well that London might be out of sync. It returns a successful response to the user, but the data is temporarily inconsistent across the globe.
And what did Instagram do?
Instagram actively chose availability and partition tolerance. They chose AP over CP.
Which means they accepted, by design, that user A in New York and user B in London will see different numbers for a few seconds.
Yes. They embraced what system designers call eventual consistency.
Eventual consistency.
It contrasts sharply with, say, a core banking system.
Right.
If I transfer $1,000 from my checking account to my savings account, the banking system must choose consistency. It is a CP system.
Because money is involved.
It absolutely cannot allow me to spend that $1,000 from my checking account if the savings account hasn't securely registered the transfer. If the network is partitioned, the bank will deny the transaction. They choose to be unavailable, to show you an error rather than be inconsistent with your money.
That makes complete sense.
Yeah.
If Instagram goes down and throws a network error, every time there's a slight hiccup in transatlantic fiber traffic,
Right.
just make sure a light count is perfectly mathematically accurate, users will abandon the app entirely. In social media, speed and the feeling that the app is working is paramount.
What is truly fascinating here is the psychological acceptance of eventual consistency in our society. We have been completely conditioned to accept slight digital inaccuracies in real-time platforms as long as the dopamine hit of the infinite scroll remains uninterrupted.
It is so true.
Think about it. You genuinely do not care if a photo has exactly 10,000 likes or 9,995 likes. You care that when you double-tap the screen, the little heart animates instantly. The user experience is tied entirely to availability, not strict consistency.
We tolerate a little bit of illusion for the sake of friction-free entertainment. And by moving to Cassandra for these write-heavy activity logs, they engineered that illusion perfectly.
You really did.
Cassandra acts as this incredibly resilient, decentralized ring of data that eventually agrees on the truth, but prioritizes keeping the app alive right now.
Exactly.
But eventually, even with Cassandra handling global writes and Redis handling memory reads and Postgres handling sharded core data, they hit another wall.
Always another wall.
And this wasn't an infrastructural wall. The servers were fine. It was a human wall. Which brings us to the shift from technical bottlenecks to organizational bottlenecks.
Ah, yes. This is where system design becomes sociology.
The reality was that the infrastructure could now handle global billion-user scale. But the code base, the actual files that the developers were typing into every day, was still a monolith.
The old Python Django monoliths from 2010.
Exactly. All the code for posts, the code for comments, direct messages, the machine learning recommendations, it was all compiled into one giant, sprawling application.
Which is a nightmare for teams.
As the company hired hundreds of new engineers, the technical architecture had outgrown the organizational architecture. They were stepping on each other's toes every single time they tried to push an update.
A bug in the comments code could accidentally take down the photo upload feature because it was all tangled together.
So they migrated from a monolithic architecture to bounded microservices.
They decomposed the application. Instead of one giant tangled block of code, they created distinct, completely independent services for specific functions. A service just for posts, a service just for comments, a service just for likes.
It is like breaking up a giant, rigid corporate mega corporation where everyone sits in one massive building and has to ask the CEO for permission to do anything.
And what do they replace it with?
Instead, you break it up into independent, highly agile startup teams. You have the comment startup. You have the like startup. They have their own offices, their own code, their own deployment schedules.
And these startups only communicate with each other via highly structured, standardized memos.
Yes, and the format of those memos evolved significantly over time to handle the scale.
Yeah.
Initially, they communicated via REST APIs using standard HTTP protocols. But later, to gain performance, they moved to gRPC for greater efficiency and speed.
Let's expand on that. Why the switch? What makes gRPC so much faster than a standard REST API?
Oh, that's a great question.
It comes down to how machines talk to each other. REST is typically text-based. It usually sends JSON payloads over HTTP 1.1. JSON is human-readable text. It literally looks like words in brackets.
Right.
This is great for a human engineer trying to debug something, but parsing text is computationally slow for computers. The machine has to read every character, parse the string, and translate it into machine logic.
Like sending a handwritten letter in the mail. You have to open the envelope, unfold the paper, read the handwriting, comprehend it, write a reply, put it in an envelope, and send it back.
Exactly. gRPC, which was originally developed by Google, uses protocol buffers instead of JSON.
What are protocol buffers?
Protocol buffers serialize the data into a highly compressed binary format. It is already in the machine's native tongue. There is no text parsing. Furthermore, gRPC runs over HTTP2, which allows for multiplexing.
Multiplexing meaning,
With the old REST over HTTP 1.1, if the comment service needed to ask the user service for 10 different profile pictures, it had to open a connection, ask for picture 1, wait for the response, ask for picture 2, wait for the response. It was sequential and blocking.
very slow.
Multiplexing allows you to send multiple requests and receive multiple responses simultaneously over a single connection.
So to extend the analogy, REST is the single letter in the mail. gRPC multiplexing is like establishing a dedicated multi-lane fiber optic highway directly between the two teams, where thousands of trucks packed with compressed binary cargo can pass each other simultaneously at light speed without ever causing a traffic jam.
Precisely. For internal microservice chatter, where these independent services are talking to each other millions of times a second just to render one single page for the user, switching from text-based REST to binary gRPC is a massive, transformative performance upgrade.
It drastically reduces the latency of those internal communications. And the way they managed all this traffic evolved as well. They moved from traditional load balancers like a proxy to Envoy proxies operating within a service mesh.
Envoy is an incredibly important piece of this puzzle. Think about the chaos of a microservices architecture. You now have hundreds of different services talking to each other constantly.
It sounds like a logistical nightmare.
It is. How do you handle retries if the like service is responding slowly? How do you encrypt the traffic so it's secure? How do you track exactly where a request is failing in a chain of 20 different service calls?
Right. Who manages all that?
Instead of forcing every single developer to write all that complex networking logic directly into their specific code, you deploy a service mesh. Envoy acts as what we call a sidecar proxy.
A sidecar proxy.
Yeah, it physically sits right next to the service on the server. It intercepts all incoming and outgoing traffic, and it handles the networking, the security, and the observability completely transparently.
That is wild. The developer just writes the business logic for comments. Envoy acts as the universal translator, the security guard, and the traffic cop entirely behind the scenes.
Oh, exactly.
And this level of decoupling, this absolute separation of concerns, is what enabled them to reach massive machine learning scale. By 2025, they were using a complex funnel architecture to process trillions of signals for Instagram Reels.
Trillions.
We are talking retrieval phases, light ranking, heavy ranking, utilizing over 1,000 individual PyTorch models. You literally cannot build a machine learning pipeline that massive inside a web server monolith. The ML team needed their own distributed compute clusters.
And this organizational shift is a perfect textbook demonstration of Conway's law.
Who's Conway?
Melvin Conway. He stated back in 1968 that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations.
Meaning, if you have a monolithic team structure where everyone reports up the same chain of command and sits in the same massive room, you will inevitably, unavoidably write monolithic, tangled code.
Exactly. If you want a decoupled, highly scalable microservices architecture, you first have to create decoupled, highly autonomous engineering teams. You align the human teams with the software services. The architecture follows the org chart.
But this raises an important question. When should a company not use microservices? Because right now, we're making it sound like microservices are the promised land, the ultimate destination for every single app ever built. But it's not true, is it?
It is absolutely not true, and adopting microservices prematurely is a lethal mistake that has killed countless startups.
Really? Lethal?
Yes. Microservices introduce a massive, punishing operational tax. You go from monitoring one single application to monitoring hundreds of them. You have to deal with distributed tracing, unpredictable network latency, and the absolute nightmare of distributed transactions.
That sounds awful.
If your team is small or your business domain is unclear, you risk creating a distributed monolith.
A distributed monolith. That sounds like the worst of both worlds.
It is the ultimate architectural failure. It happens when you break your code into separate services, but they are still so deeply logically entangled that if you want to update the user service, you are also forced to update, test, and deploy the payment service at the exact same time.
Oh, man.
You get all the network latency and complexity of microservices, but absolutely zero of the independent deployability and speed you were hoping for.
So how did Instagram avoid the distributed monolith trap? How did they know where to draw the lines?
By adhering to strict domain-driven design principles, you have to define clear, rigorous service boundaries. A bounded context.
Like setting fences?
Right. The comments service should own absolutely everything about comments, including its own separate database schema. It should not be reaching directly into the user database to check a profile picture. It should only interact via defined APIs.
And if you fail to do that?
If you get the boundaries wrong, the whole system becomes a tangled, chatty mess of network calls. Instagram succeeded because their domain, social media interactions, decomposes very logically. Comments don't need to know how the recommendation algorithm works. They just need to store text.
Okay, so we have traversed a massive decade of engineering. We have hundreds of independent microservices. We have multiple data centers operating globally, Cassandra databases asynchronously syncing, Redis caches keeping the feeds lightning fast, Envoy proxies managing the invisible mesh of traffic.
The scale is immense.
The sheer number of moving parts is astronomical. Which brings us to our final exploration: fault tolerance, elasticity, and chaos engineering.
My favorite topic.
When you have a billion users and thousands upon thousands of servers, the law of probability dictates that something, somewhere, is always breaking. A hard drive is failing, a network switch is burning out, a memory module is corrupting.
It is a mathematical certainty.
How do you keep the app online during New Year's Eve, which is the highest traffic night of the entire year, when hundreds of millions of people are uploading champagne toasts at the exact same moment?
You accept the reality that failure is inevitable. You stop trying to prevent every single error, and you design for elasticity and rapid recovery.
Looking at their cloud strategy, Instagram utilized extreme elasticity via AWS auto-scaling. This allowed them to automatically provision new EC2 instances during massive traffic spikes.
It's important to understand that elasticity is distinct from scalability.
What's the difference?
Scalability is just the ability to handle growth over time. Elasticity is the ability to automatically expand and contract resources based on immediate real-time demand.
Oh, the contract part is key.
Yes. On New Year's Eve, AWS autoscaling continuously monitors the CPU utilization and the incoming request queues. As the countdown approaches midnight and traffic begins to surge exponentially, the system automatically, without human intervention, spins up hundreds or thousands of new servers.
That is so cool.
And just as importantly, when everyone goes to sleep on January 1st and traffic drops, it terminates those servers so Instagram stops paying for them.
And to optimize those massive infrastructure costs, they intelligently blended spot instances with reserved capacity.
Yes, cloud economics.
I assume reserved capacity is like signing a long-term, 12-month lease on an apartment to get a cheap baseline rent while spot instances are like booking a cheap hotel room at the very last minute that the hotel is just trying to fill before the night is over.
That is a very apt analogy. Reserved instances provide a reliable, heavily discounted baseline for the normal, everyday traffic you know you will always have. Spot instances are spare cloud capacity that Amazon has sitting idle in its data centers.
So it's cheap.
Amazon auctions this compute power off at massive discounts, sometimes 90% off. But the catch is Amazon can pull the plug on those spot instances with only a 2-minute warning if a full-paying customer needs them.
Whoa, just a 2-minute warning.
Yep. By architecting their microservices to be stateless, meaning the server itself holds no permanent data, Instagram could run their heavy compute workloads on these spot instances extremely cheaply. They knew that if Amazon terminated a spot instance mid-task, the system would gracefully handle it, and another instance would seamlessly take its place without the user ever noticing a glitch.
But to guarantee that a user never notices a server suddenly dying, here is where it gets really mind-bending.
Yeah.
To ensure true resilience, they embraced chaos engineering.
Yes.
This is the practice of deliberately maliciously injecting failures into your own production system to break things on purpose.
I have to admit, when you first learn about this, it instills a deep sense of disbelief.
It does.
You have 1 billion users, your app is a global communication utility, and your own engineers are writing scripts to intentionally pull the plug on live servers just to see what happens. It sounds deeply counterintuitive, almost reckless, but it is the most sophisticated form of risk management in distributed systems. Pioneered largely by Netflix with their famous Simian Army and Chaos Monkey tools, chaos engineering completely shifts the engineering mindset from prevention to recovery.
Meaning, you stop trying to build an impenetrable fortress wall that can never be breached, and instead you constantly train your army to fight incredibly well once the wall inevitably falls.
Precisely. You cannot prevent all failures in a massive distributed system. The permutations of what can go wrong across millions of lines of code and thousands of physical machines are infinite. So you must optimize for recovery.
You have to practice failing.
If you wait for a natural disaster or a massive organic traffic spike to test if your backup systems work, you will fail. Chaos engineering forces developers to build systems that automatically heal and route around damage because they know that a script is actively hunting down and terminating their servers during normal business hours.
So the developer, writing the code for the comments service, knows for a fact that Chaos Monkey might randomly kill their primary database at 2:00 p.m. on a Tuesday.
Yep.
So they are forced, out of sheer self-preservation, to build retries, fallbacks, and automated circuit breakers into their code from day one.
Exactly. It forces defensive engineering. And there are several specific architectural patterns they use to survive this constant, intentional chaos. The bulkhead pattern, for example.
Like on a submarine.
Yeah.
If one compartment of the sub floods, you seal the heavy steel doors so the water can't spread and the whole sub doesn't sink.
Yes. In software architecture, this means isolating your resources. If the machine learning recommendation engine suddenly starts consuming massive amounts of CPU because of a bad code push, the bulkhead pattern ensures it is physically and logically restricted.
It doesn't drag everything else down.
Right. It cannot steal CPU cycles from the core photo uploading service. The failure is contained to its specific compartment. The recommendations might load slowly, but users can still post photos.
And circuit breakers. How do those work in software?
It mimics the physical electrical safeguards in your house. If Service A is calling Service B, and Service B starts timing out or throwing errors or acting sluggish, Service A will trip its internal circuit breaker. It immediately stops sending requests to Service B entirely.
So it cuts the cord.
It gives Service B time to breathe and recover, rather than pounding it with continuous traffic and causing a cascading failure that brings down the entire network.
And what happens to the human user holding the phone when that circuit breaker trips deep in the data center? Let's say the circuit breaker for the comment service trips. Does the Instagram app just instantly crash on my screen?
That leads to the final, most elegant concept in modern system design: graceful degradation.
I love that phrase.
If the comments microservice completely fails and the circuit breaker trips to protect the network, the app does not crash. Instead, the system gracefully degrades its functionality. You can still open the app, you can still scroll smoothly through your feed, you can still see high-resolution photos.
But no comments.
The comments section beneath the photo might just show a little spinning loading wheel, or the comment button might just temporarily disappear entirely. The core functionality, the infinite scroll, the visual dopamine hit, is preserved by sacrificing a non-critical feature.
It consciously chooses partial functionality over complete catastrophic failure. It is better to have a silent photo than a crashed app that boots you back to your home screen.
Always.
That is phenomenal. It really changes how you look at the app when something doesn't load quite right. It's not necessarily a bug or bad code. It might be the system actively, intelligently saving its own life.
It is the ultimate expression of system resilience, surviving not by being rigid, static, and unbreakable like a concrete skyscraper, but by being flexible, isolated, and highly adaptive.
We have covered an immense amount of ground today. Let's briefly recap this incredible journey for everyone listening. We started in 2010 with a tiny, scrappy monolith running on a single Postgres database, relying purely on vertical scaling and the simplicity of off-the-shelf tools to handle early explosive growth.
From 3 guys in a room?
All right, and when the data exploded and vertical scaling failed, we saw the genius of horizontal database sharding and hash-based partitioning, packing timestamp and logical shard data into a custom 64-bit ID using embedded database logic to completely avoid costly network hops.
We then explored the critical shift from disk to memory, using Redis to cache pre-computed feeds and bypass the database entirely, introducing the complexities of the cache-aside pattern and event-based invalidation.
From there, we scaled globally. We tackled the reality of the CAP theorem, realizing that for a massive social network, availability and eventual consistency through multi-datacenter replication in Cassandra is vastly superior to strict banking-level consistency.
Very different priorities.
Then, to solve the human bottleneck of developers stepping on each other, we broke the monolith. We instituted Conway's Law, migrating to bounded independent microservices communicating via lightning-fast binary gRPC and Envoy proxies in a service mesh.
And finally, we looked at how to make that massive, complex web of services truly unbreakable, embracing cloud elasticity, the economics of spot instances, and the intentional, controlled destruction of chaos engineering.
To force the implementation of bulkheads, circuit breakers, and graceful degradation.
What a journey.
It is a staggering evolution. But I want to leave you, our listener, with a lingering speculative idea that builds on everything we've uncovered in today's exploration. We spent the last hour seeing how Instagram evolved from a rigid central monolith, a single database chef in a single food truck, into this fluid, distributed mesh of microservices that literally heal themselves, that shed non-essential functions to survive stress and adapt dynamically to traffic loads.
It's organic.
In many ways, it behaves less like traditional software and much more like the human brain, which uses distributed synapses rather than a central hard drive to store memories and route signals.
A biological analogy is remarkably fitting for highly advanced distributed systems. They display emergent behavior.
Right. So as we push further into the future, toward AI-assisted architecture and edge computing running right on your individual devices, will the system designs of the future stop looking like traditional software altogether?
It's very possible.
Will the next big app even be engineered in the way we understand it, or will it be grown like a biological organism? Will we see networks that organically shift their own logical shards, autonomously mutate their own caching policies, and spin up their own protective bulkheads without a human ever writing the code, automatically adapting to survive traffic predators and environmental changes?
That is a wild thought.
Just think back to our opening thought. We started by talking about building physical skyscrapers versus digital ones. Maybe the ultimate digital building isn't a skyscraper at all. Maybe it's a forest. An interconnected living ecosystem that responds, adapts, and survives the chaos without a central architect pulling every single string.
Beautifully said.
Something to think about the next time you open an app, double-tap a photo, and take that perfectly smooth, infinite scroll entirely for granted. Thank you for taking this deep dive with us.
It has been a true pleasure unpacking the architecture behind the magic.
Until next time, keep questioning how the world around you actually works. Stay curious.